Hello and welcome. Let's continue with our lecture on mathematical methods. We have looked at some of the aspects of curvilinear geometry and we have looked at the covariant differentiation. The covariant differentiation is naturally connected to the geometry, that is metric in the case of Riemann geometry. Once we have this connection, we can have a uniquely defined covariant derivative in terms of connection, which is expressed by the metric. To start with, this geometry allows us to do physics in curved space-time. The idea is a lot simpler than what you think it is, but one has to take it with a little bit of intuitive manner rather than the rigorous fashion. In this lecture, we will focus on the geometric aspects of physics, or we also have a look at how we go about applying the concept which we learn to the physics problems, especially generalizing the Newton's law, and then we look at the local inertial frames and then connect various aspects of the geometry and the coordinate transformation. Let's continue with the lecture. Let's do some physics on curved space-time or curved space. The difference here is whether it is a Riemannian geometry or whether it is a pseudo-Riemannian. In the case of space-time, we have one signature change, and that allows to have a null direction, that is a direction along which light propagate, that is called the pseudo-Riemannian. In contrast, if you have positive definite distance, then it is called the Riemannian. We are basically interested to extend our laws of physics to pseudo-Riemannian geometry, that is with the special theory of relativity which is already incorporated. Now we have defined the covariant derivative operator which transform like a tensor. Let's do a bit of an adventure. Let's leave our safe hold of flat space-time and liberate ourselves into curved space-time or pseudo-Riemannian geometry. We have already defined covariant derivative. I have flashed this equation several times just to get this imprinted on your mind. The covariant derivative has two terms. One is a ordinary differentiation or a partial differentiation, and the second term, which is called the connection term, ensures that the hence defined the covariant derivative is transformed like a tensor. So the connection in general is an arbitrary, allows you to define the covariant derivative. However, we are sticking to the Riemannian geometry where the connection is closely associated with geometry or the metric. In this case, connection is defined in terms of partial differentiation of a metric component as given by this equation here. So in this case, this connection is called the Christoffel symbol. In order to do physics on curved space-time or Riemannian geometry, we need to have an equation expressing the laws of physics in a covariant form. Now we see that most of the time we express the laws of physics in terms of ordinary differentiation or the partial differentiation. However, we know it is not covariant, so we have a new derivative operator which is covariant derivative. So all we need to do is simply replace the ordinary differentiation with the covariant differentiation, and then we have a laws of physics which are covariant and simply carried on to the curved space-time. This looks rather a simple prescription and you might think that it is a bit of a fishy too. However, it can be done with a very rigorous approach with the help of Hilbert-Einstein action. However, that is beyond the scope of this course. So let's take this as an intuitive step by simply replacing the ordinary differentiation by covariant differentiation. However, we need to be a bit careful and do this step by step, and we will proceed doing this. The first idea which we need in order to do this is idea of directional derivative. When we have vector field in the covariant form or contravariant form, directional derivative of a tensor field U, which can be tensor of any higher rank both in the contravariant and covariant. The directional derivative of tensor U with respect to vector T alpha is given as the dot product between the vector T alpha and the covariant derivative of U. that is T alpha delta alpha of u, that can be expressed in terms of component as T alpha delta alpha into u and its comp. So that is how it goes. One can write down this in terms of a covariant or contravariant vector. Since in the Riemannian geometry derivative of metric tensor is 0, we can easily raise this and we can simply write this equation as T alpha delta alpha u, that is where your delta alpha is given by u of alpha beta delta beta. So this is how we have the expression for the directional derivative. However, from the physics point of view, it is important to have geometric connection. That is, if we have T alpha as a tangent vector to any given curve, that is, we can write T alpha as a dx by ds of x alpha. That is a tangent vector, and we can now define the directional derivative of u along a curve, which is the same as directional derivative of any tensor field along the tangent vector. And geometrically, view this as a curve is parameterized by arc length parameter, and the tangent vector is given as a dxa by ds, and the T alpha is tangent vector, which is given as a dxa by ds, which gives the tangent to the curve xs. And the expression of a directional derivative along the curve or tangent vector is basically denoted by capital D by ds in order not to confuse with the ordinary differentiation, that is d by ds, where s is a arc length parameter. So in order to differentiate this, we use a different notation. Keep in mind that this expression explicitly means that taking the covariant derivative of the tensor field u and then taking the dot product with the T alpha, which is tangent vector, and here it is explicitly written that the covariant derivative of tensor field u, and that is taken the dot product with the dxa by ds, which is a tangent. So that gives the directional derivative of any tensor field with respect to a curve or with respect to the tangent vector of that curve. Now with this notation, the first things comes into mind is that the acceleration. In physics, we often call the tangent vector as a velocity vector, that is a T alpha is equal to dx alpha by ds, which may be called as a velocity if the curve is instantaneous position of the particle with respect to the proper time. Now we can take tangent vector and the directional derivative of tangent vector with itself, or the directional derivative of tangent vector along the curve, denote acceleration, and we have a alpha, that is capital D alpha by ds is equal to T beta delta beta T alpha, that is taken the covariant derivative of a tangent vector T alpha and take the dot product with the T alpha, and that is what you get. And we can explicitly express the covariant derivative in terms of the connection coefficient, and what we have is first is a partial differential of a T alpha with respect to x beta, and then we have a gamma term. Together, all we can write it as ordinary differentiation of the tangent vector with respect to arc length, that is a dt alpha by ds plus gamma alpha beta gamma t beta t gamma. So really we can see that tangent vector and acceleration vector, it is a derivative of the tangent vector, is represented in this figure. Some nice simplification happens when we use arc length parameter. That is, we have already seen that if you use arc length parameter, then the tangent vector becomes unit vector, or the norm of tangent vector is 1, that is T alpha is equal to 1. It is a general result from differentiation is that if you have vector T alpha which has a constant norm, then its derivative is always orthogonal to the vector T alpha itself. We have this figure here, the curve which is represented by x of s is the arc length parameter, then we have a tangent vector dx alpha by ds is equal to T alpha, then we differentiate it again along tangent vector, that is we take the covariant derivative and take the dot product, and then we get the acceleration which is always orthogonal to the tangent vector itself, which is a fairly useful entity in the physics, because in the case of Newton's laws of motion, we know that the acceleration which is equated to the force. Let's go ahead and define the geodesics. Let us consider 2 points P and Q in a Riemannian space or pseudo-Riemannian space. Let us consider a set of all curves starting from P and ending at Q. Now our goal is to find out the curve which has shortest distance from P to Q. This is interesting optimization problem. This is common in the case of Lagrange equation of motion. Now what is the meaning by the distance between the point? We have an infinitesimal displacement along the curve which is given by ds. We simply integrate that from the point P to Q. That gives us distance along the curve x alpha of s. So that is what we mean by distance between the point P and Q, and that is what we want to minimize. Of course, you know that the minimization is essentially an optimization problem, and obtained solution could be either minimal or maximal. We are optimizing this distance. Let's start with square of the distance. In the Riemannian geometry is given by the length element ds square is equal to g alpha beta dx alpha dx beta, where g alpha beta is metric tensor. So we simply use our standard physics way of doing the differentiation, that is, we divide this by ds and multiplied by ds square. Tricks by which mathematician may not be very happy. However, in physics, common doing this. Dx alpha by ds is a tangent vector t alpha, then we get the result that g alpha beta is equal to t alpha into t beta into ds square. So this is essentially is the distance element along the curve. We can also write this as a slightly different notation which we have used. In our notation, the tangent vector or the 4 velocity represent as a x dot alpha or x dot beta. We write that as a g alpha beta as x dot alpha into x dot beta into ds square. We have to optimize. The optimization is basically done with the length element, that is s is equal to integral from p to q the square root of g alpha beta dx dot alpha into x dot beta into ds. However, instead of carrying on with this, we do an alternative, optimize ds square, so that we can get rid of some extra term which involving the ds and assume the optimization of ds and ds square would give you the same result. With that notation, we write arc length element, it should have been s. We optimize integral p to q g alpha beta x dot alpha x dot beta into ds. This is standard optimization problem when it comes to the Lagrange equation of motion. This is what we do for a moving particle. This is basically is kinetic energy. That's the reason we are optimizing the ds square and not the ds. So the kinetic energy optimization, or it is also a Lagrangian, and solution to this optimization, we know that Lagrange equation of motion can be written as dx square d alpha by ds.
There is a square missing here, and this should be ds square.
Then gamma alpha beta gamma x dot beta into x dot gamma is equal to 0. That is also equal to d by ds of t alpha plus gamma alpha beta gamma t beta t gamma. So this is a result which we have shown in tutorial problem. We have taken the kinetic energy of this form, the quadratic in the velocity, and then shown that the Lagrange equation of motion would result in this, what is called the geodesic equation of motion. So this is elaborate calculation we some time back have done, and you are worried why we have been doing such a lengthy calculation to get the equation of motion in specific form. The only reason for doing that is to identify the Lagrange equation of motion exactly gives the geodesic equation of motion, and the basic connection is the distance and the kinetic energy can be written with this form. Let's continue with the geodesic motion. We have a curve which satisfying the differential equation d square x alpha divided by ds square plus gamma alpha beta gamma x dot beta x dot gamma is equal to 0. So this is an optimal curve which optimize the distance between the point P and Q. Now we see that in general you may say that it is a minimization. It is not true in general. It could be minimization or maximization. If the geometry is infinite, then this minimize the distance. If you have a finite geometry such as a sphere, then result could be both maximal as well as a minimal. In the case of sphere, you see that the geodesics are the great circles. So you take 2 points, then connect it through the great circle, you have two segments. One goes around the sphere, and that would be maximizing the distance. On the other hand, other shorter distance, which gives you the minimal distance. So you could have both minima as well as a maxima in a given geometry, and connection here is given by the Christoffel symbol with its standard definition. Basically, in terms of our notation, saying that the geodesic equation is simply represented by the acceleration of the curve being set to 0 is what gives the geodesic curve. In the case of mechanics, you would say that the force-free particle would be going along the geodesic. You may not use word force, then you can simply say that the free particle will be moving along the geodesic. So that is one of the interesting results. Now, in short, what we have is the curve for which acceleration is 0 gives us the optimal path between 2 points in the Riemannian geometry. You can come at this result by optimizing the distance, or you can optimize the Lagrangian, and eventually the result is state that if the acceleration is 0, then it gives you optimal path between the two given points P and Q. Let us look at them in terms of the Newton's equation of motion, or a generalized equation of motion in a curved space-time. Let x alpha of S be a world line of particle in the Riemannian geometry. Any time-like curve or curve along which a particle moves in the space-time is called its world line. That's just a name, but it is somehow picked up. It represents how it propagates in the space-time. Then the velocity of this particle or the tangent vector is given as a du alpha, often represented, at least in this course, we represent it as a u alpha, which represents the force velocity dx alpha by ds, which gives the tangent vector or the velocity vector. On the other hand, we can also have an acceleration, that is the directional derivative of the force velocity along the force velocity itself. So that gives the acceleration. You have a path traveled by time-like particle that is given by x of alpha, and then you have a tangent vector which is u alpha, which is given by dx alpha by ds, and then you take a directional derivative, that is a alpha is equal to capital D u alpha by ds, that is expressed in terms of ordinary derivative and the gammas, because the ordinary derivative now have to be replaced by the covariant derivative, and resulting expression can be written as du alpha by ds plus gamma alpha beta gamma u beta u gamma. So this is basically acceleration, and we can again explicitly write down in terms of coordinate of the world line, that is d square x alpha by ds square plus gamma alpha beta gamma dx beta by ds dx gamma by ds. That is the acceleration of a particle. And we also know that if we use arc length parameter, it's always orthogonal to the force velocity of the particle. And then when we set the particle acceleration to 0, we get the geodesic motion, that is d square x alpha by ds square plus gamma alpha beta dx beta by ds dx gamma by ds is equal to 0. So this may be called generalized Newton's laws of motion, where you are calculating now the directional derivative with covariant derivative rather than the ordinary derivative, and you have a connection built in which makes the whole equation covariant, and this is basically is a generalization of Newton's laws of motion. If one want to think it in a restricted fashion, sometimes we want to draw analogy by looking as if it is simple Newton's law in an inertial frame. Then we will have a d square x alpha by ds, and then because of the curved space-time, it looks like there is going to be a force acting on it, which depends on the square of the velocity through the connection, and that is we can call is an effective force acting on the particle in the curved space-time. But often one do not want to have this analogy, because this would be our equation of motion. Each time you do not want to call it some effective force. Now onwards, when you say geodesic motion, you understand that it is a particle is moving in curved space-time. If gamma is 0, 0, then you have inertial frame, and otherwise gamma will always contribute to the motion of particle. Even in the cases such as a spherical polar or plane polar coordinate, these gammas are non-zero because of the nature of the coordinate curves, and then leads to an effective force. But we really don't want to talk in terms of effective force. We tell that the particle is free and moving along geodesy. We have seen that how Newton's law can be generalized to curved space-time by simply replacing the ordinary derivative by covariant derivative. Can we do that electrodynamics too? The answer is simply yes. We can transform relativistic electrodynamic equation or relativistic Maxwell's equation to the curved space-time with this correspondent. We simply have to replace the partial differentiation by covariant differentiation and result in a Maxwell's equation in the curved space-time or in the Riemannian geometry. However, this correspondence cannot be done for the non-relativistic theory, because in the non-relativistic theory we have a time coming as an absolute quantity, and that cannot be translated to any of the relativistic curved or flat. So it is essential to have a relativistic theory to do this correspondence going from flat space-time to curved space-time. In the case of Maxwell's equation, I am simply writing the equation only. If necessary, we can have an additional 2 or 3 lectures on the relativistic Maxwell's equation. In the relativistic Maxwell's equation, neither electric field nor magnetic field is important. You might have seen that both of them can be made zero in an arbitrary frame, while it is non-zero in other frames. So this is not possible for a tensor. So this simply says that neither electric field nor magnetic field is covariant. The most fundamental quantity or the dynamical variable in the case of relativistic Maxwell's equation is a vector potential. The first component of vector potential is the electric charge, and then you have a 3-dimensional magnetic vector potential coming as a spatial component. Once we have that, we can define what is called the Maxwell tensor, which is a second rank tensor, which is given as a del mu a nu minus del nu a mu. You can clearly see f mu nu is an antisymmetric tensor, and in this special case it doesn't matter whether you use a ordinary derivative or a covariant derivative. So this rule is simply can be carried forward flat space-time to curved space-time, simply replacing the ordinary differentiation by the covariant differentiation. Now A is the vector potential. Once we set L mu to be partial differentiation x mu, then we have relativistic Maxwell's equation in the flat space-time. Now the source-free Maxwell's equations written with the set of 2 equations, that is divergence of f mu nu is 0, that is del mu f mu nu is equal to 0. The last one is a commutation relation, that is differentiate f mu nu and then take the cyclic permutation, and that goes to 0, and these two gives you the source-free Maxwell's equation. On the other hand, Maxwell's equation with the 4 current density J mu, electric charge density comes as a 0th component, and then current density comes as the spatial component, and here the source Maxwell's equation is given by divergence of f mu nu is equal to J mu, that is delta mu f mu nu is equal to J mu. Other equation remains same. The commutation relation of Maxwell tensor is always going to be 0, whether it is a source or no source. From these 2 equation or 3 equation in this case, you can reproduce all of the Maxwell's equation, and that is why these 2 forms the fundamental. In this case, you can replace covariant differentiation by partial differentiation, and then you would get the Maxwell's equation in the flat space-time. Next comes an important idea of local inertial frame. We have seen that the correspondence between relativistic physics and the physics on curved space-time is done through this correspondence where you replace the ordinary differentiation by covariant differentiation. How we can go from a physics on curved space-time back to flat space-time? This is a concept where we have a local flatness. In the case of Riemannian geometry, we can set gamma to be 0 and then make a frame locally inertial or local flat. This is possible only because gammas are not tensor quantity. If gammas were tensor quantity, then if it is 0 in one coordinate system, then it would be 0 in all coordinate system. Since we want to have a coordinate system locally where gamma is 0, on the other hand, in general, gamma need not be 0, so we can specially construct such coordinate system. Such coordinate systems are called local inertial frame. The local coordinate system, either we have to have gamma is equal to 0 or the first derivative of metric tensors have to be 0. This can only be done in the Riemann space with the condition that connection is a symmetric in the lower indices. That is, basically we need to have a relation between metric tensor and the connection. If that is not there, then it is not easy to do that. We can do a transformation by which the partial differential of a metric is 0. Again, it is possible because the partial differentials are not tensors, so you can have them 0 in one coordinate system and non-zero in another coordinate system. These two conditions eventually are leads to the same, whether you impose them on the connection or whether you impose them on the metric tensor. Purely a mathematical aspect, whether you can find such thing. We know that conceptually it can be done. I briefly sketch the outline. How to do is you have a transformation rule for the second rank covariant metric, which you apply it on the metric tensor and take the differentiation and then set to 0. So you basically left out with the term which is like this, which you can use them to manipulate such that the derivative of this to be 0 while it is not 0 on the x coordinate system. Easier approach is to directly impose this condition on gamma. Here essentially you are having a gamma prime is 0, have a two coordinate system x prime and x, in which them say x prime has a gamma 0 and the other one which do not have gamma 0. In this case, we know how the gamma transform. This is a term which we said caused the trouble. Now this is exactly the term which is going to help us. If the gamma prime is 0 while gamma is not 0, then we impose this condition and we end up having a expression for the coordinate transformation or the derivative of coordinate transformation to the gamma. So it is basically coming from this term, and we can rewrite this equation by cancelling the common term. If you are uncomfortable with this, cancelling the common term, you can simply multiply by dx mu by dx prime mu on the both side and then simplify, impose the condition, you get a delta mu nu, and then you can rewrite the equation in this form. This basically gives the condition on the coordinate transformation such that the gamma is 0 in one coordinate system and gamma is not 0 in other coordinate system, and this kind of a coordinate system is what we call locally flat or a locally inertial frame. So this is going to play important role in converting all our equations which can be derived in the curvilinear geometry and then come back to the inertial frame by using a local inertial frame or simply by setting gamma to be 0. Loophole here intentionally because it is simply a mathematical subject. You can get this condition integrated and get the exact expression for the transformation, which is not really essential. You can simply replace the covariant derivative by ordinary derivative and get away with it. These are the derivation just to show that formally it can be done and there can be a coordinate transformation which allows you to do this. This is what gives us the freedom to do physics on curved spacetime, that is to transfer all our equations which are derived on the Minkowski spacetime or relativistic equations to curved spacetime by this correspondence that you replace partial differentiation by covariant differentiation, or you can come from the curved spacetime to flat spacetime with the idea of local flatness or replace the covariant differentiation by partial differentiation. We have seen in detail how we have done this for Newton's laws of motion. First we took the Newton's laws of motion. We had a non-relativistic case of this equation, that is rate of change of momentum is equal to force. Then we generalized this equation to the relativistic case where we have a 4 momentum, its derivative is equated to the 4 force. We actually have not done it, but we set the force to 0 and then dp by ds is what we have is a expression which equated to 0. Now we can move on to curved spacetime, replace the ordinary derivative with covariant derivative. That is a new notation which we have used, is a capital D, that is a d mu by ds is equal to f mu. So this is a road which we have taken to convert Newton's equation of motion to curvilinear geometry. Only for the relativistic case we can do that. Any equation can be converted from flat to curvilinear geometry. We have done this independently to the Lagrange equation of motion, which is generally applicable to curvilinear coordinate system. So we did not have to do anything. It has a built into the covariant differentiation and all of the things in it. That is what we have shown, that the Lagrange equation of motion directly equated to the geodesic equation of motion after some elaborate simplification. This leads to natural question that whether we can convert Newton's law of gravitation to curved space-time. The answer is no, because Newton's laws of gravity is non-relativistic. There is no role for speed of light built into it, so it cannot generally be done. So you know that it is a Laplace equation, which is a three-dimensional equation. The generalization of Laplacian from 3 dimensions to 4 dimensions is a wave equation, but it is not clear whether it can be straight away done in that way. One needs a little bit more elaboration for that. So non-relativistic case cannot be simply converted to curved space-time. On the other hand, we have a relativistic quantum mechanics which can be done with this approach. If the answer is satisfactory to all people who are working in that, it may not be true. Because what we have, rigorous way of doing it is through the least action principle. In this case, this principle is called the Hilbert-Einstein action, through which what is called the minimal action. That means that there is no interaction between the quantum fields and the curvature itself. On the other hand, you may want to have some interaction. In such case, such equations cannot be obtained from this generalization. One has to independently solve them using the Hilbert-Einstein's action and putting all the physics into it. Some physics may be absent. However, at the zeroth stage, one may obtain the suitable limits of a general theory by going to curved space-time or using this correspondence of replacing the partial differentiation by covariant differentiation, go to curved space-time. This may give us a limited understanding which may take us a step closer to generalizing any theory to the curved space-time through an independent action. However, it may or may not be able to do it. Till that, we have an approximate way of doing it. It is basically like looking at a vast picture in terms of a narrow scope of local freedom. That is wisely said in a context that how set of blind men interpret the elephant. Since they are not able to see the full picture with the touching them, each one has their own interpretation which may not match with the global picture. That would be basically what we will be doing if we take the idea of carrying on physics from flat space-time to curved space-time by simply replacing the partial differentiation by covariant differentiation. We will be missing the global picture. That is why we need to have a global picture, and that cannot obtain using this local correspondence. Let me stop here